Thanks, Bill. Yeah, actually, when you work in the Arctic, you get lots of good stories to work with, everything from being attacked by grizzly bears to having where you take off from the airport, and as you go down the runway, you hear a thud. You get in the air, and you have the co-pilot come back and lie on the floor between all the passengers, get up, go back to the front, and all you hear is Yellowknife, come in Yellowknife. And then everything goes dead quiet. And a little later on, they come back and they say, well, we think we have everything, so we're just going to continue on. Because they didn't find anything on the runway. So we just continued on to our destination, did a low flyover. The wheels were there. The wings still seemed to be there. And so we landed. No problem. But that's typical things. When you see all your jet fuel being discharged out of the wingtips, it makes you wonder what the problem is. And the problem with that one that we had was that they didn't tell us anything until we were ready to land. So everybody that knew what was going on didn't know how serious the issue was. But when we landed at full speed, and then once we landed, they braked. And all the emergency equipment was sitting out there on the edge of the runway, waiting to pick us up with the stretchers and whatnot. Yes, those were the good days. Anyways, what I'm going to talk today is using what we refer to as underground thermal energy storage as a renewable energy that sits beneath our feet. And it doesn't matter where you are, we have energy just sitting there waiting to be used. And underground thermal energy storage, or UTES, the acronym, actually includes a whole host of different types of technologies. But they all involve thermal energy storage within the ground. If we go back and we look at, and I know this is dated 1997, but Canada lags behind updating its statistics in government. When you look at the distribution of energy that's consumed on a residential basis, and I'll start residential here, you see that 60% is space heating, 20% water heating, your appliances and lighting is another 18%, and cooling is 2%. So it's really the heating load. Of course, this is Canada, snow and ice all year round. So heating is a big thing. But when you look at that distribution, you see that the space heating in particular, and to some degree the water cooling, is all done using hydrocarbons, at least for the most part. There may be some homes that have electrical heat, but usually oil or natural gas is the main thing for heating. And water heating, again, usually natural gas, can be electric. When we look at institutional energy demand, also from 97, we find that space heating is not quite as high. It's only 52%. The cooling is up to 5% now. Water heating is only 7%, but it's the lighting and all that auxiliary equipment and auxiliary motors that add to the load. And often you'll get a building, and with the high-tech industries that we have now, we're constantly running computers. And there's probably lots of computers in this building. And just the computers alone tend to create a tremendous amount of heat. You can probably heat the building just from the computers being left on, but that's really electrical energy being transformed into heat energy and then radiating out and heating the building. Often the buildings get too warm just from all the computers that are in it. So buildings that do have that kind of equipment load often require a lot of cooling, even in the middle of wintertime. Now, the space heating and I'll say the water cooling, as I've said, hydrocarbons, fossil fuels, for the most part, is what we're using to deal with that energy, or the type of energy that we're using. The rest of it, which makes up, 30% or so, is basically electrical energy that we're using. A lot of the renewable energy technologies that you hear about these days, whether it be wind or solar or biomass, although biomass is a little bit different, but a lot of them they're trying to look at replacing or adding to electrical generation because we're reaching peak capacity with electricity. Hydrocarbons are a non-renewable resource, and so the largest part of our energy load is actually with this non-renewable resource, and if we can turn it around and actually replace some of those hydrocarbons that are being used with a renewable energy source, then over the long term, that's going to be a good thing. And that's why with the underground thermal energy storage, we're focused really on the replacement of hydrocarbons. Because I work up in the Arctic most of the time, of course, my geothermal gradient, this is just a diagram showing the gradient of temperature within the ground. In this case, you'll see the numbers at the top are primarily negative. So I'm dealing with permafrost regions. But it doesn't matter about the temperature at the top other than to say temperature is increasing from left to right. I've got a pointer here. So from the left side to the right side is increasing temperature. Near ground surface here, you actually get changes in the temperature of the ground throughout the year. In the wintertime, the temperatures will drop because of cold air temperatures. In the summertime, solar heating of the ground surface, you'll find that the temperatures increase. And so they get considerably warmer in the summer than what they are in the winter in near surface. As you go deeper into the ground, the temperatures become constant year-round. They still vary with depth, going from there to there, and the deeper you go, the higher the temperature. And the geothermal gradient, basically heat from the interior of the Earth, radiating outward toward the surface of the Earth, and then radiating out into space. Typical geothermal gradients are in the range of 25 to 30 degrees centigrade per kilometer. Do I have to convert back to? Sorry, I forgot. I'm from a metric country. I will try and use, that old system of feet and inches and degrees Fahrenheit whenever possible, but forgive me, I'm so used to using these temperatures now. But 2.5, 3 degrees centigrade per 100 meters. And 100 meters, roughly 330 feet. So it's going to increase with depth. It's also going to change depending on where you are, latitude-wise. So this is actually from an older journal, and when you look at it up in the north here, these are in Fahrenheit. It's saying that average groundwater temperatures are as low as 37 degrees Fahrenheit, and by the time you get down to Florida, you're up to 77 degrees Fahrenheit. Now, whether this is really an accurate map, I won't say that it is. In middle of Illinois here, it would put you as being between 52 and 57. So it's, I think, a little on the high side, but maybe not too bad. I think you had said earlier 55?
55, about 200 foot down.
Okay. So that's not too bad. Up in Ottawa, which is, right about up in here, it's saying 42. We're actually around 49, 50 degrees. I think something with the Adirondacks here is probably influencing it, the higher altitude, pulling things down. So we're actually up in this area, sitting at close to 50 Fahrenheit. So you get a distribution like this across the country, and you can look at it and say, well, I'm here in Illinois, and my ground temperature, average ground temperature, fairly shallow, along with the groundwater, is going to be a relatively constant 55 degrees Fahrenheit, year-round. So what can you do with that? Can you do anything with it? Well, if you take a typical building, in the wintertime, you've got to put heat into that building to keep it warm because the outside air temperature is a little below what you consider the comfort zone. And during the summertime, you have to cool the building. solar radiation or because of the equipment you have in it, dictates that the temperature again rises above the comfort zone, and therefore you need to cool it. Traditionally, down in the basement of the building, you'd have a furnace for heating during the winter time, and during the summer you'd have an air conditioner or you'd have a chiller unit. A mechanical box operating the same way as an air conditioner really, to cool the building down. And it's the building air that you're cooling down or warming up. And we have down here ground temperatures that are relatively constant throughout the year. So the question is, can we tie together this constant ground temperature and make use of it within our building for space heating or for space cooling? I'm going to say that yellow line is a little high for me. It's showing it being around 25 degrees centigrade. I would say room temperature should be 20 degrees centigrade. I prefer mine even a little cooler than that. And if you bring that bar down a little bit more, it actually improves the diagram. These two lines going up and down is talking minimum and maximum air temperature, average monthly temperatures from January through to December. So in the wintertime, it's cold. We'll say it averages between minus 10, minus 20. Obviously, you're going to have those minus 30, minus 40 degree days, and you might have the 0 degree day. But it's going to average down in the range between these two lines. Down here, your air temperature is less than the groundwater temperature, which I'll say for Ottawa is 10 degrees centigrade. So if the air temperature during the winter is lower than the groundwater temperature, you should be able to take that groundwater and heat up, take heat out of the groundwater and heat up the air in your building. And during the summertime, right here, when air temperatures get above the groundwater temperature, you should be able to use the groundwater as a sink for that heat. In other words, take heat out of the building air and dump it into the groundwater. And remember, I'm saying groundwater here, but the groundwater is in thermal equilibrium with the ground. And both the ground and the groundwater have a relatively constant temperature year-round. Okay? Now, the difference between your groundwater temperature and your room temperature, on the heating side, you'd have to bump that up, either by using a heat pump or by designing something else that'll give you that extra bit of heat. Heat pumps, this is larger industrial size heat pump, is simply used to give you that additional heat. And I'm not going to say more about them because I'm not an engineer. If we look at the different types of underground thermal energy storage systems that exist, here's our buildings up here. If we have an aquifer underneath our building, let's say we're talking this building here, if there's an aquifer underneath the building, we could potentially drill a couple of wells into the aquifer, and we could use one for pumping during one season, pull the water out, put it through a heat exchanger in the building, and then bring the water back and put it back into the aquifer. And if that would be during the winter season, where we're taking this water, dumping heat into the building. So our groundwater now is colder because we've taken heat out of it. So what we're putting back in the ground is cold water. And then during the summertime, if we actually pump from this well, bring it up, put it across the heat exchanger, now we're taking heat from the building, dumping it into the water, so we're raising the temperature of the groundwater, and we put it back into the aquifer, we create a warm area. And we can go back and forth on a seasonal basis. If we don't have an aquifer, with groundwater readily available. And instead we have fine-grained sediments, maybe silts and clays, or a fine-grained glacial till, or maybe we have massive crystalline basement complex, big granite complex or something like that, massive, essentially no water. We can put in a series of boreholes closely spaced, and we can run piping down within the borehole, back up, connect them all together, and create, in a relatively small area, a thermal energy store. And once again, we can create a hot store and we can create a cold store. You need a lot of boreholes, but you can do it. We can go further and say, if we're in an area where we had mining activity and we've got underground mining that's now been completed, those old mines have been back flooded with groundwater over the years, we can take those old mine workings, which are really open caverns, and we can use those similar to the way we used the aquifer here, and have different areas of the mine as a hot store and a cold store. And failing all of that, we could dig a pit in the ground and contain a fluid there to be able to store our energy. Now I'm going to focus on the aquifer system simply because that's the one that I'm most familiar with and that I've done the most work with, although I have been doing some preliminary studies on cavern storage. In Canada, we've got thousands and thousands of old mines that are now abandoned, and so we're looking at whether or not we can use those as energy storage areas. So if we just look at the aquifer one, we then have to look at what kind of aquifer do we have? Is it a confined aquifer, confined between a fine-grained basement complex and some silts and clays? Or is it an unconfined aquifer near surface where we've got a water table? It's going to be more susceptible to contamination from the surface, but if we're not using it for drinking water, maybe that's okay. What is the gradient like? Gradient talking about the flow of groundwater. Groundwater flows just like an electric current or like heat. If you've got a little campfire burning, it's really hot if you're close, and it gets cooler the further you move back. But the heat is radiating from that campfire outward. With groundwater flow, you're flowing from an area of high groundwater levels to areas of low groundwater levels. If you have a low gradient, such as in this example, you can keep the hot and the cold plumes close together or close to the well. But if the gradient is fairly high and you have rapid flow of water, then those plumes that you're trying to create will actually migrate down gradient and away from your well. So you have to determine the geological characteristics and the hydrogeological characteristics of your site. In this example, these little open lenses here are potentially small aquifers that are not aerially extensive, but they might be suitable if you've got a small application. So basically, you've got your buildings, you've got a heat pump, a heat exchanger, and you've got your geology. The subsurface, you've got wells in them, and again, you pump out of your wells across one side of the heat exchanger and back into the ground. Because the groundwater for these UTES systems is coming from the ground and you're putting it back into the ground, it's considered as an open loop system. Whereas where I had the boreholes close together, a borehole thermal energy storage is closed loop because all of your fluid is kept within piping. It never actually goes back in the ground. You just radiate the heat back into the ground. So at Carleton, we started a project back in the mid-'80s, and we had grad students working on this project, and we really started with, can we do something other than putting in a new chiller to replace one that had met its life expectancy? And so we started to look at thermal energy storage and whether or not it was feasible to do. Now, the Carleton campus, this area in here is the actual academic campus. That's residences out that way. The administration building, the first one that we wanted to work on, was this little building here. And that's the one that had the high heat load, needed a lot of cooling, even in the wintertime, because of all the computers. And of course, the first question was, well, you've got a river here, there's a canal and a lake here, why don't you just use the surface water? Well, the surface water doesn't give you a constant temperature. In the wintertime, it's close to 0 degrees C. And in the summertime, it's probably up around 20 degrees C. So you don't get that constant temperature. And the temperature, you know, if you are going to have a differential, you want it to go the other way. You'd rather have 0 degree water in the summer and 20 degree water in the winter. So it doesn't work. Plus, there's all kinds of environmental regulations that you can get into. So we stayed away from it. I'll just point out right here, this little bit of white are some rapids that I'm going to show you in a second. From a geological point of view and trying to understand the campus here and the geology and the hydrogeology, that area right there is the only outcrop that is present in the entire campus. And when we started this project, we had no idea really what the geology or the hydrogeology were like in any detailed sense. The other complicating factor is that Carleton happens to sit right on one of the main faults in the Ottawa area. So not only do we have a poor understanding of the geology we do know is that we're sitting on a fault. And it's amazing. Administrators are great at picking up little tidbits of information. And when I had to go to a Board of Governors meeting and we were talking about re-injecting water, the first thing they said, or one of the first things they said, was, well, because we've got these faults, is that meaning that you're going to reactivate the faults and we're going to start having earthquakes here? And I said, no, I'd have to increase the pressure quite a bit, but if you want me to experiment and do research on it, I'd be more than happy. But they didn't buy. Here's the rapids that I had just shown you. The rocks across here, these are sedimentary rocks, Ordovician in age. They're actually tilted to the east. We're looking south up that way. So that's to the east. Normal faulting with the east side down. And so we've got bedrock close to surface at this particular location. If you go just off the picture here, you won't see any more bedrock. And in fact, if you drill a hole there, you'd find that you have to go almost 200 feet to get to bedrock. And it's a vertical escarpment. When you look at the campus, everything is flat. The ground surface is flat. But when you start looking at the geology, you find that there's a lot of variation. And that variation is because of old river channels cutting gorges through the area. This is just to show bedrock surface in contours, meters above sea level. This is the high area in here, where we're 55 to 60 meters above sea level. And then here it drops off quite a bit, very quickly. And we also have some buried valleys under the campus that nobody ever knew about. But by doing the geological investigations, we start to find them. And when we put our data together and create a block diagram, the river would be flowing along here, and here's the bedrock surface just dropping off. And back in through here is another one of the buried valleys that go across. So very complex geology, both in terms of the bedrock and in terms of the superficial unconsolidated geology. What we found as we were drilling was that the bottom of these valleys were actually filled with not glacial fluid, but fluvial debris, coarse sands, boulders, and then above that we had glacial deposits that had basically infilled the valleys right to surface, and then the whole surface is covered with clay from a large marine sea that existed there. It was actually part of the ocean covering it. So we had clay and then glacial deposits and then fluvial deposits underneath. And the fluvial deposits were from rivers. Once you get all of your existing data pulled together, and those maps were originally generated using existing databases, finding all the information. And a lot of it was geotechnical information. Every building that gets constructed, you have to drill holes, first of all, to look at the footings and what kind of foundations do you need for the building. And that is information collected by civil engineers that usually goes into a report that the architect looks at, and then it gets filed. And in the case of Carleton, it got filed in the circular files that were long gone. And so we had to go back to the engineers, the civil engineers, the consultants, and recreate all of the data from their files because they were smart enough to hold on to them. There's a wealth of information out there that usually nobody has ever looked at. Once you get all of the existing information together, then you've got to go and actually drill a well. You've got to drill a test well. And so you bring in the drill rig. And you start drilling. Hopefully, you're going to hit water. When we started the project, we were talking about doing the one building, and the engineer told us we needed 300 gallons per minute of water flow. So we figured out where to drill our test well. We went out and we started drilling, and we hit water at our expected depths. Everything was fine, but then we hit more water. And one of the biggest problems with these projects is when you're too successful. Because when you hit more water, then all of a sudden people say, well, we should have a bigger project. And we went from a 300 gallon per minute, one building project, to a 1,600 gallon per minute, 10 building project overnight, which is not the way to go. Take notes. Once you do that, everything gets magnified and the scale gets bigger and bigger. And if you're going through this for the first time, you want to learn on the small scale, and then as you become experienced, you ramp up. Well, finding lots of water was great in one way, but not so great in the other way, in that we started to lose control of the project. We couldn't keep it to the small project that we really wanted. But finding the water is really just the start. Oh, that's just another shot showing the water. We were covering this whole area, trying to get any of the drilling bits, the rock debris and whatnot to settle out. So we spread it out over the grass area before it went to a holding pond. We had too much water for our original containment system up there. It was just flowing too quickly. The one well, we had flow rates of up to 3,000 gallons per minute, which nobody ever expected when we started this project. So this whole area basically became flooded and covered with drilling sediment debris as we sort of let it filter out, and then we had cleaner water to deal with. Once you've got the water, then you have to look at trying to understand your whole system and put it together as a package, knowing that you've got the water isn't enough. So we used borehole geophysics. We had actually run some surface geophysics earlier. We used borehole geophysics, logging the boreholes for temperature and other parameters. And we even ran some of the temperature logs while we were testing wells. So at P23, we're running a test, and you can see that the temperature variation occurs while you're pumping at another well. And the variations that you start to see, such as in here and down here, and then a sudden jump back across, start to tell you something about how the groundwater is moving, preferentially where it's moving within your aquifer complex. These are rock aquifers, they're fractured, so they're fairly complex. And we needed to understand how the flow was taking place. Doing the other geophysics then helped us, because we knew we had faults on campus, helped us take our initial 5 wells and figure out where we were in the stratigraphic sequence through the campus. That helped us to figure out which wells were going to be connected to one another. And we were drilling in different types of material. So our wells, the red dots here, put in the context across campus for this first phase. These are the 5 wells I just showed you. That was the really high producer over there. Put in the context of the main faults going across the campus. In reality, all the way from the faults here to over here is a fault zone, and it's all brecciated and broken up. But those are the major faults on campus. Once you get outside of this central zone, there really isn't much in the way of fault activity. So if you go over here, there's not much fracturing, and the amount of water you get drops off dramatically. You go over here, you're into really deep overburden, and the drilling costs went up. And because we were focused on this part of the campus, we didn't go there. We also installed monitoring wells, multi-level monitoring wells with lots of tubing, finished at different depths so we could monitor what was happening at different depths within the ground. And we had to run a number of tests where we were pumping wells and where we were re-injecting water into the wells. This pole here is really to measure pressure. This is an injection well. And it doesn't matter how careful you are. These pipelines were running across the campus, the university campus. They went up over roadways and across so buses could go underneath and whatnot. We marked them off really well. We put up barriers and whatnot. It still didn't stop the students from coming out after being in the pub half the night, getting on their bicycles, racing down the pathway and running headfirst into the pipeline and doing a front flip and smearing themselves across the pavement. It's a challenge when you're working on a university campus. Just the safety aspects. But if you're starting with a small project close to the building, you shouldn't have those problems. The other thing you get from students, there's no students here, right? The broken beer bottles and whatnot that they then shove down the wells if you don't seal them at night. Anyways, we did lots of testing. And the testing was important to tell us about the hydrogeology. It was also important to tell us about the importance of knowing what you have to do when you case a well. Standard practice at home, I'm not sure what it is here, is that you run your casing through the overburden and say 3 meters into competent bedrock, and you seal it, you grout it, and it's open borehole below that because the rock will stay open without putting a screen or anything in. Well, we thought we were being cautious, and we ran our casing 10 meters into bedrock. But because of those irregularities in the bedrock surface, we found that we put a well in, and it was up on the high ground. Just if you move over laterally, you were actually into one of these buried valleys. And when we ran one of our first tests, injection, and it wasn't this well, but it was raining out lightly as we started injecting water into the well. And when we started to get more water bubbling up out of the ground, then was raining down upon us, we knew we had some problems. And we had to go back and re-sleeve that well. We figured out what the problem was. We had to re-sleeve it and sleeve it down so the casing was below the bottom of the buried valley. Because we were getting a lateral short circuit. It just went out the bottom of the casing, laterally across into the valley, and then started flowing and made its way back to surface. Some pumping results. The top line here is the actual pumping well, the drawdown in meters. So as time increases, the amount of drawdown increases. And then we've got two observation wells. You can see this one is actually very close in terms of drawdown to the pumping well. And it's almost 500 meters away, so half a kilometer away from the pumping well. This other observation well is only a quarter of a kilometer away. This one is half the distance away from the pumping well than this one. Now, normally you would think that the pumping well is going to have the most drawdown, and as you move away from the pumping well, the drawdown will get less and less and less. So the observation well furthest away should have the least amount of drawdown. And that's not what we see here. And we don't see that because these two wells are preferentially connected because of the fracture system. So flow is not uniform in all directions. There's a preference to flow directions. So we have to take that into account in trying to understand our system. And so we have to create models, groundwater models. The denser line areas are representing the faults, which are areas of higher flow. And then the rest of the grid in here is the more massive bedrock, where we still have bedding, we still have some fractures there, but a lower density, so lower flow rate. And we model it, and we have to look at things like the heat that we put into the ground. How far does it extend during the heating season? So over a 6-month period, we've got multiple wells here, some pumping, some re-injecting, and our production rate, 265 liters per second. So if you roughly divide that by 4, so what are we at? Say 65, 70 US gallons per second. So probably in the order of 4,000 US gallons per minute. And after 6 months, that's what our heat plumes would look like under the campus. But that's assuming that our aquifer is fairly uniform in terms of flow throughout that whole aquifer. And when you look at it, we say that the aquifer thickness is 60 meters. Well, if we're dealing with fractures and the flow is preferentially within the fractures, it's not through the whole 60 meters, it's going to be something less than that. So what happens to our heat plumes if instead of 60 meters, we use 6 meters as our aquifer thickness? Remember, we're modeling. And you can see same pumping rates, much more extensive heat plume migration. And where we've got migration along a fault, it's going to be long and narrow. Where we're off a fault, it's going to be more circular. So you have to get all your existing data of the geology. You have to understand the geology as best you can. You have to drill, get more information about the geology. You have to do all of your hydrogeology, your testing of the wells, figuring out what's happening. You also have to do water chemistry. And then you have to put it all together into your models and really see if you can understand what's happening. Because if you can't understand what's happening, it can create problems down the road. But if you know what you're doing, and if you pull together your multidisciplinary team, It's not that difficult to make it work. But I've talked about some of the problems. So why should we bother doing this? Why don't we just buy the chiller, pull it off the shelf, and install it and forget about it? Well, there's a number of environmental benefits to going to this type of technology. There's a reduction in the consumption of natural gas, of oil, and of electricity. Remember I said I was focusing on the fossil fuels, the hydrocarbons, but you do in fact reduce your consumption of electricity. Instead of operating chillers, which use a lot of electricity, or you can get natural gas chillers, but instead of using a lot of electricity on those chillers, and that electricity is during peak time, if you want to cool this building with a chiller, you pretty well have to operate it during the daytime when the people are here. I don't know whether in Illinois you've gone to differential electrical rates, but we're certainly seeing them in Canada now where during peak times you pay more per kilowatt hour than you do when you move to off-peak times. And you're going to see that coming, and the differential is going to get bigger and bigger. Places like Japan, it's on the order of a factor of 10 between daytime and nighttime. In Ottawa, they've now installed smart meters in every house so that the hydro company can actually tell how much electricity you're using at any minute of the day. And our pricing structure is now going to differential rates. Yeah, but they don't want you running the dishwasher, during the 6 o'clock to 8 o'clock time. They want you to run it in the middle of the night while you're sleeping. So that's coming. Lower CO2, in fact, with this system, you basically have no CO2 emissions. You also reduce your sulfur and your nitrogen compound emissions, so air quality improves. And I noticed in today's edition of USA Today, they were talking about all these schools throughout the U.S. and air quality issues because of surrounding industries and what's coming out of their smokestacks. And that there's literally hundreds and hundreds of schools where the students are breathing in toxic fumes. So air quality is an issue. And with these energy storage systems, you reduce a lot of emissions, if not get rid of them altogether. CFCs are now banned, but there's other refrigerants that are being used in the chillers, and you get away from all of those. So you reduce that. It's a renewable resource if you re-inject the water back into the aquifer. If you don't, if you pull it out and you simply dump it in the local ditch, it's not what I would call renewable. If you're doing it on a really small scale, you can say, oh, I can do this forever and the aquifer is not going to run dry. But if you do it on a larger and larger scale and more people want to do it, then your aquifer will run dry. And right now I understand that most of the industries here are using cooling towers, and the cooling tower water is basically groundwater. And with the cooling towers, most of that water evaporates. They're evaporative coolers. So that's a groundwater resource that's basically being evaporated, it's being lost, and you're not using it as a renewable resource. When you go to this type of system, you eliminate cooling towers and all the chemicals that are associated with them. So you're saving water in that sense. And even if you aren't using groundwater for your cooling tower, you're then using municipal water. And the cost of treating water so that it's potable is fairly expensive. And water rates are going up. At least they are at home. And they're going to be going up a lot more. And you don't necessarily need to have that quality of water to do the cooling tower, but you're using the source that's already there and you're just tapping into it. So we found that with a thermal energy system, we can also reduce the amount of municipal water we were using. And it's non-toxic to plants and animals. So if you're into environmental areas, it's great that way. Some of the other benefits, it actually does have lower operating costs. There are costs associated with installing it in the first place, but the actual operating costs are much lower than a traditional system. It's less sensitive to energy price variations because you're cutting back on the use of electricity, you're cutting back on the use of fossil fuels. It doesn't matter whether the conventional energy prices go through the roof and oil goes to $140 a barrel. You eliminate your sensitivity to those prices. The amount of electricity you're using is much, much less, and you're using a renewable resource that you're maintaining as a renewable resource. So it's there for you to be able to use next year and the year after. You can offload from peak demand periods. You can load shift, and you can manage your system so that you're not using electricity during those peak times. The systems are quite adaptable, and you can have hybrids. There's one in Alberta right now that they've just installed an entire subdivision. They put in the energy system, and then they've added solar power or solar panels to collect thermal energy. And that thermal energy that they collect, they then put it underground and store it. So that in the wintertime, they now have a hot store, they can pull that solar thermal energy from the summer when it's nice and sunny, and they put underground, they can bring it back up and use it to heat the houses in the subdivision. And by doing that, they can actually heat up their store sufficiently that they don't have to worry about heat pumps. They can just do a direct transfer of heat. And they tend to have higher efficiencies than a lot of the traditional equipment. There are some cons, and I'm going to be right up front in mentioning them. Upfront capital costs. The systems tend to be more expensive to install in the first place, but presumably through the lower operating costs, you're going to get that money back over a short period of time, and then you're going to have savings benefits afterwards. But initially, you have to come up with the money. Unfamiliar new technology. People don't really understand it, and so they shy away from it. And I found this with engineers. You know, as I said at the beginning, it's easy for an engineer to go along and say, well, I need so many tons of cooling. I can open my book. This is the size of chiller I need. I can call company X. I can order it, and next week it'll be here. We can hook it in, and the story's done. Doing this type of thing isn't as easy. And most places will have engineers on staff. But how many places have a geologist or a hydrogeologist on staff? The university does. The state survey here does. But most places don't. That means if they want to do this, they have to call somebody with the expertise. They don't have it in-house. And as soon as they don't have it in-house, it becomes foreign technology. And it's a barrier that you have to overcome. There's potential interference with other water users if you're in an area where lots of people are making use of the water. However, by re-injecting, you're not actually consuming the water the way companies are with their cooling towers. They're pumping the water out, it's evaporating, it's gone. If there's anybody else living around them, they have a major impact on those other users. Whereas here, the impact is actually pretty small. And if you design your system properly, you can minimize that impact. But it's certainly less than the water towers or the water cooler. Requires knowledge of the subsurface geology. This comes back again to not having the in-house staff. Space. If you've got an aquifer, you need to space your wells out. And that requires having some land. And some people may say, I don't have enough. Regulations, there's more and more regulations all the time coming into play. The traditional equipment, everybody knows how they operate, and so everybody knows what the regulations are. But when you go into a newer technology like this, the regulations are still being written. And so there's a lot of uncertainty over what do I have to do. Hopefully, we're getting to the point where that's understood and people do know what to do. But we're not quite there yet. And finally, you need to know your baseline conditions. When we talk about savings, lower operating costs, what are we comparing that to? And quite often, many facilities don't have any real idea of what their energy costs are or how they're split over the time of day or where they might actually be able to save money. Getting over that hurdle is also a major one. So they're cons, but they're not insurmountable. Okay? And if you don't have an aquifer, I mean, that's the biggest con of all for an aquifer thermal energy storage system. If you don't have an aquifer, well, then you have to look at going to something like one of these borehole systems, or maybe you've got an old mine, so you use that. But no matter what the situation is, it's possible to adapt one of these technologies, usually either A or B, to where you're located. And so you have the potential to get energy from beneath your feet, locally. And you can make it renewable if you design it properly. But the aquifer systems are by far the most efficient, the lowest cost, they have the lowest operating costs. So if you have the aquifer, if you have the potential for using it, then that's the one to really work with. And I'll leave it at that. Thanks.
Any questions for Fred?
Yes. I don't know, because I'm not in the financial side of it. We had projected. No, it operated for a period of time, and then we had a change of administration, and overnight the project was stopped. Not for technical reasons, but for financial reasons. The university went through, I think in the U.S. you have a thing of all the universities being rated by some of the popular magazines, you know, which one is the best and which one is the worst and whatnot. And Carleton got caught up in not providing very good answers to the first national survey in Canada, and they got ranked as the bottom of the list, which really impacted on their enrollments. And suddenly they were into a financial crisis, and lots of things got terminated. At the time, we were estimating that our savings were on the order of $500,000 per year for the portion that we were operating. But I don't have any detailed costs on that. Okay? I want to emphasize it was not a technical issue. It was a financial issue, and the administration, that's one of the key things. You have to have the people, everybody, to be on board and keep them on board.
What's the difference between the duct borehole system and the traditional geothermal system?
Okay, if I just go, okay. The duct borehole system is simply, well, duct or borehole, either one, simply a series of boreholes, closely spaced. You have your piping looped down and back up, then into the next borehole, back up. It's called closed loop. A lot of people think of that as a traditional geothermal. And The word duct is used more in Europe, and in North America we tend to use borehole. But it's a closed loop system. It can occupy a very small footprint. Often what they'll do is they'll take the parking lot, and before it gets paved and whatnot, or they'll rip up the pavement, put in all the boreholes, hook the system up, and pave over it, and nobody even knows that it's there.
So it is really more of a traditional.
It's more of a traditional system. And it depends on your local geology conditions as to which one you go to.